Swayam Prabha. Digital India. Educated India.
So in my previous lecture, I have discussed about the different test methodology, your field test, then the laboratory test to determine the dynamic soil properties. And I have also discussed about the model test like centrifuge test, Heck table test, and I have discussed about their scaling laws also. In this lecture, I will discuss about the stress strain behavior of cyclically loaded soil. Okay, so now if we see the stress strain behavior of a cyclically loaded soil, so we can see that if this is your stress strain behavior of a soil, and if I join the point of the tips of this hysteresis loop, because these loops are called hysteresis loops, and if the locus of points corresponding to the tips of hysteresis loop of various strain amplitude is called backbone curve. That means if I join the tips of these loops, then this blue curve is called the backbone curve. Okay, this is backbone curve. So that means we have number of hysteresis loops and with different strain amplitudes, and then if I join the tips of these loops, then I will get the backbone curve. Now before I go to this backbone curve, let me explain about the different how to get the different shear modulus from a hysteresis loop. For example, this is a hysteresis loop which is your shear stress versus shear strain. Here also it is shear stress versus shear strain. Now in this hysteresis loop, if you see that its modulus value is changing on every point. So that means it is changing on every point. So suppose if I take the modulus value on this point, so I suppose this point I want to determine the modulus value. So this modulus value will give you, if I take a tangent on that particular point, I will get the shear modulus on this. If I take the slope of that tangent, I will get the shear modulus, because this is shear strain versus shear stress or stress versus strain. So if I want to determine the shear modulus at this point. So if I take a tangent on that point, then I will get a modulus, and that is called the tangential modulus. But here the another modulus value is being introduced or can be used, that is called second modulus. Okay, what is second modulus? Suppose for a particular your strain, this strain value is say 1, and if I join this tip and then this origin, and now if I take the slope, then I will get another shear modulus, and that is called second shear modulus. That is called G second shear modulus. So this every point your G10 is changing, your shear modulus is changing on every point over the loop. Okay. Now the second shear modulus is the average shear modulus of that particular loop. Clear? So that means the second shear modulus is the average shear modulus that we can use for our analysis purpose. So that means right now I have discussed two shear modulus. One is the tangential shear modulus, one which is changing over the every point of the loop. Another is the second shear modulus, which is the average shear modulus of that particular loop. So now, if I want to represent the non-linearity nature of the soil, then generally I can use two models. One is your equivalent linear model that I am discussing right now. Another is the non-linear model. So in equivalence linear model, in simplified form, we represent the nonlinearity of the soil. So in that case, we use the second modulus. So for our equivalent linear model, we use G sec, and obviously for non-linear model or nonlinear analysis, we use G tan, because this is the shear modulus which is changing over the loop. But in the equivalent, we are doing it in the simplified form that nonlinearity is represented. So that's why the average shear modulus is been taken. And there is another type of model, that is the linear model or linear analysis. There we use G max or the G0, or that is the shear modulus for low strain condition. So G max is the low strain shear modulus, because here it is a linear analysis, a linear model. So that means here we can say that it is a linear analysis, so soil is in low strain condition. So it is linear behavior. But whenever we go for the non-linear response of the soil or non-linear behavior of the soil, then we use equivalent linear model or the non-linear model. So equivalent, both the cases we represent the non-linearity of the soil, but in the equivalent linear model we do it in a simplified form. So that is clear when we will use the which shear modulus. So now I have discussed the three shear modulus, that is the G max, which is the low strain shear modulus, that is the equivalent shear modulus, G sec, which is equivalent linear model, and the non-linear model we use the G tan. In the non-linear model also we can represent this system plot, but we also follow the backbone curve. Now I will go to the backbone curve portion. Now in the equivalent linear model, we get this backbone curve. Now if I get this backbone curve, then I will get, this is my backbone curve. That is your shear stress, shear strain and shear stress. So this is my backbone curve. This is also backbone curve. Okay. So now the initial slope of the backbone curve, that will give me one shear modulus, that is G max and G naught, and at any point, so I can get another shear modulus. This is G sec. This one, so that means I can draw in number of your shear modulus, second shear modulus. So this is my one shear modulus. This is one shear modulus. Okay, this is one second shear modulus. So this is another second shear modulus. Then this is your another second shear modulus, and this one is another second shear modulus. So every point on the backbone curve you can get a second shear modulus and corresponding to different strain amplitude, corresponding to this strain amplitude. This is the strain amplitude, this is also another strain amplitude. So this is say strain 4, this is strain 3, second 1. So I will get second shear modulus at every point, and you can see that your shear modulus is not constant, it is changing as your strain changes. So same thing you can do it here also, that you can calculate your different shear modulus, second shear modulus at any point, okay, corresponding to say this is your strain 1, this is your strain 2, this is your strain 3, and so on. Clear? That means your shear modulus is changing with strain, or it is changing and it is not constant, and you can say this modulus value actually decreases as we increase the strain. Okay, so now if I draw in a different way, that if I draw a backbone curve, say another way I can represent that if I draw a backbone curve, so I can say that this is one hysteresis loop and this is also another hysteresis loop. This is also another hysteresis loop. So here this is my shear modulus, here this is my second shear modulus, and so on it will change. Okay, so that means here I can calculate the second shear modulus from this backbone curve, and this second shear modulus changes with strain. So this is my equivalent linear model. Now if I go for non-linear model, there also I want to produce that this hysteresis loop, this stress strain behavior, and with the help of this backbone curve. It will follow that backbone curve, but at the same time I can generate that hysteresis loop or this stress strain plot. So, and that I will discuss in my later lectures, that how I will use that your non-linear model also. Now that means it is clear how I will calculate the Gmax, and I will discuss in detail that from a backbone curve how I will calculate the G value for any strain level in my next lectures. And I will also discuss the nonlinear models about in the coming lectures about the triaxial test, because I am talking about the shear modulus, that I will get the your shear modulus, that means I will get it from the stress versus strain plot. But in the triaxial I will get the axial strain versus deviatoric stress or deviator stress. I will not get the shear stress versus shear strain directly. From the cyclic simple shear test, I will directly get the shear stress versus shear strain. But from the triaxial test, which is very common, I will get deviator stress versus axial strain. Now from there, how I will calculate the shear modulus. So there are two methods or two way I can do this. That one is your the method which is very simple, and another one I will do some assumptions, and then I will do determine the shear modulus. First I will do the simple one, that if it's triaxial test, you first calculate the elastic modulus, which is very easy to calculate, because you calculate the from these particular loops. Here also your elastic modulus changes with the every point on the loop. So you can change take average elastic modulus, so that is E sec. So E sec is the average elastic modulus for this particular loop. Now the E sec or E value you can calculate, I am just writing E here, so that will be sigma d divided by axial strain, or sigma d divided by axial strain. Now once you get the E, then you can convert it to G by using these expression 1 plus 2 mu. It means here first you calculate the E value, okay, and if you use the same way you can calculate the E sec, second Young's modulus, then you convert it to shear modulus, and that way you can get the shear modulus also from the triaxial. But that sometimes this triaxial data, this David-Torr stress versus axial strain, is converted to shear stress versus shear strain. How it is been done? Generally that it been done in this assumption that your shear stress is equal to half of David-Torr stress. How it possible? That you know that shear stress is equal to sigma 1 dash minus sigma 3 dash divided by 2 into sine 2 theta. So this will be my David-Torr stress divided by 2 into sine 2 theta. Now if your theta is 45 degree, then I can write that shear stress is equal to half of David-Torr stress, but it is valid if your theta is 45 degree. Remember that. So that there is a condition that this is valid if theta is 45 degree. So now if this is the case that shear stress equal to David-Torr stress divided by 2, and you know that shear modulus is equal to del tau by shear stress by shear strain, okay, or G is equal to shear stress by shear strain, and G, you know that G is equal to E divided by 2 1 plus mu. Now if I convert that, then it will be shear stress versus shear strain, that is equal to E divided by 2 1 plus mu. Okay. Now this E is nothing but David-Torr stress divided by axial strain 1 by 2 1 plus mu. Okay. Now my David-Torr stress is your 2 tau. David-Torr stress is 2 tau divided by axial strain 1 by 2 1 plus mu. So your this tau will cancel, and finally I can write that my shear stress is equal to axial shear strain is equal to axial strain into 1 plus mu. So this is the another condition by which you can convert the David-Stokes stress versus axial strain plot to shear stress versus shear strain plot. Okay, so this is your David-Stokes stress divided by 2. So this is the condition. Okay, so that means one method is directly you can calculate the E and from there you will get the G. Another, you convert this stress strain plot from David-Stokes stress to axial strain and then convert it to your shear stress versus shear strain, and from there you calculate your values like I have discussed. Okay, so this is for the shear modulus part that I have discussed. About the linear mod, when you use which shear modulus for linear analysis or the equivalent linear analysis and for the non-linear analysis, that I have discussed. And now I will also discuss that the damping ratio. How we will calculate the damping ratio from a hysteresis loop. So it is the damping ratio calculation is that your damping ratio is WD divided by 4 pi Ws. What is WD? WD is the dissipated energy in one cycle or loading cycle, and Ws is the maximum stored energy. Okay, so this damping ratio can be written as 1 by pi the area of loop A dash A, which is A dash A, this is A, this is A dash. So that means the area of this loop. Okay. This is B, say, this is O, this is B dash. The area of this loop divided by the area of triangle OAB plus area of triangle OA dash B dash. Now, if both the triangles area are same, then I can write that this is 1 by 2 pi area of loop A dash A divided by 2 the area of triangle OAB. Okay, or I can write 1 by 2 pi the area of loop A dash A divided by area of triangle OAB. Okay, so that means you can write, or I can draw this hatch line . Okay, so this that means the damping ratio I can calculate by this 1 by this will be 4 pi. So that 1 by 4 pi area of this loop for a particular loop and the area of this of the triangle. So this is for a particular strain level, say strain 1. Now the question is, these conversion technique for this to determine the damping ratio for equivalent linear approach. So this equation is valid for if it is a closed loop, say, and if both these triangles are same. But there may be a situation where you will find that these loops may not be a closed loop, this can be open loop, the area of these triangles may not be the same. Okay, so in that case it is recommended that this equivalent linear approach, if it is a very high strain level, and in all these difficulties you will get mostly very high strain level, where this equivalent linear approach basically overestimate the stored energy. So that means if it overestimate the stored energy, maximum stored energy, then what will happen? The damping ratio value will reduce. So that means you have to be very careful to use this equivalent linear approach to calculate the damping ratio if the strain level is very high. For example, this if it is say more than 1%, then it will because of the highly non-linear nature of the soil, that your maximum stored energy is been overestimated if I use the equivalent linear approach. Because the reason is that, as I mentioned, in the equivalent linear approach, what we are doing? We are representing the non-linearity of the soil, but in a simplified form. So that means if we use this approach for a very highly non-linear soil, then this simplified form, this approach actually overestimates the maximum stored energy. And if it is overestimates the maximum stored energy, then your damping ratio will be reduced. I will get the very low value of damping. Say that if it is a very high strain level condition, then you have to be very careful before you use that equivalent linear approach to calculate the damping ratio. So I have given you one reference on paper that you will get the different approaches that is used for high strain damping ratio calculation, so that you can see from this paper. So this is the preliminary idea that I have given about the different approach, that means the linear approach, non-linear approach, equivalent linear approach. Okay, and then in the next class I will discuss in detail for equivalent linear approach how I will get the shear modulus value for different strain level. And then in my future lectures I will discuss about the non-linear model also. I will get the stress strain plot for non-linear model, which will also follow the backbone curve. So thank you.